Ladies and gentlemen, a very warm welcome to the Royal Society and the programme that we held on Friday lunchtimes of general history of science talks. A couple of other usual announcements, I'm afraid. If I could ask you to switch off your mobile phones while the talk is in progress, and do switch them off rather than leave them on quiet. Also, as part of the talks program, we have a couple coming up, one on Palmer's penguins in the Antarctic, and that will be on the 28th of November, and a talk on water on the 5th of December. The conference on Doctor of Enlightenment, Dr. Thomas Beddoes, is booking up, so if anyone would like to come along to that, it's on the 12th of December. You'd be very welcome, but let us know fairly quickly. Well, now, to our main speaker for today. Dr. Anna Maria Roos is a very well-known historian of science and of magic too, I think. Based at the Wellcome unit at Oxford University. She's written very widely indeed. Her last book was The Salt of the Earth, Natural Philosophy, Medicine and Chemistry in England, 1650 to 1750. She is a contributor to Notes and Records of the Royal Society and published a very recent paper on her discovery of medical sigils in the Oldenburg correspondence. An interesting read if you get the chance, do have a look at it. Now, she's currently researching a book on Martin Lister, the Spider-Man of the title. Lister is a fascinating figure from the early history of the Royal Society. Natural historian, he had his fingers in many kinds of activities, including shells, insects, and we'll hear about some of them today. And Anna will be publishing a book in 2010, we think, which will have the same title of Spider-Man, so do look out for that when it's published. It will be very good. Now, we're very fortunate to have her as a speaker, so please, a warm welcome.
Greetings. I'm very honored to speak to you today, and I would like to thank several people that helped make this presentation possible. First of all, I'd like to thank Felicity Henderson, who's quietly sitting in the back of the audience, who organizes this series in History of Science. It's always a pleasure and a privilege for scholars. We spend a lot of time in libraries, and it's lovely for us to actually get to speak to the public about what we do. I'd like to thank Keith Moore, Head of Library and Information Services, who's always been just invaluable in pulling out all the many documents and helping me out with my research. And then a few other people, Robert Fox, Editor of Notes and Records, Lisa Jardine, and Patricia Farah, all fantastic scholars and mentors to me in my process in learning about the history of science. So without further ado, let's talk about Spider-Man. This is the only portrait that we have of Martin Lister. It's from an untraced oil painting. It's based on an old black and white photograph that mysteriously has appeared on Wikipedia. Nobody seems to know where it came from. So if anybody finds this in grandmother's loft, would you please tell me? Because I'd be really interested to hear if anybody has this painting. I've spent 2 years of looking around for it. He is the father of the discipline of arachnology, spiders, and also conchology. He founded the science of the study of mollusks. And what we're going to do in this talk today is we're going to look a bit at his biography. We're going to discuss why this early virtuoso and physician was of such great importance to the early Royal Society, and a bit why it's been a bit neglected in scholarly studies to this date. And then we're going to focus on some of his lesser-known achievements, namely his invention of the histogram and the geologic stratigraphic map. So he had a lot of interests indeed. We're going to do a little bit of his biography first. As many of you know, the Aylesbury Vale in Buckinghamshire is an area of very deeply green farmland, and the nearest high point is Coombe Hill in the Chilterns, and red kites and yellow hammers and firecrests feed on the flora, which grow on Coombe Hill's alkali moorlands. And the hill offers local school children some of the best sledging in that part of England, so I've been told. Near this idyllic spot, Martin Lister was born in 1638 near Radclive, and this is a picture of the parish church. It's described as a small but neat and cleanly village. It's perched on a cliff of reddish soil that overlooks the river Ouse. And the parish register indicates that he was baptized at the small church of St. John the Evangelist on April 11th, 1639, and the original baptismal font is still there, which was a big thrill for me to go and say, that's where my guy was baptized. The 13th century structure is really quite lovely. It's got its original crenellated tower and Elizabethan pews, and I noted that the balustrade work on it is exactly the same as the manor house behind it, Radclive Manor, as well as Prince's Risborough Manor, which is a few miles away, so the same local craftsman was making his rounds. Now, though it would be really convenient for the historian, and I would say this particular historian, to say, oh, well, you know, he lived in that nice little manor house right behind the church, unfortunately, that isn't the case. It belonged to New College, Oxford, and the Listers were not sub-lessees of the New College. Where he was, I'm not entirely sure, but I have a surmise about this. I think the likely possibility is that they were living with his maternal uncle, Sir John Temple, who had a manor house close by in Stowe, and who was apparently in a number of legal scrapes as Radclive Manor over water rights in the ancient manorial mill. Sir John was diverting a brook that belonged to his neighbors onto his own property, and that's why he appeared in the records. Sir John was the brother of Lister's mother, Lady Susannah Temple. There's several portraits of her extant. This one is done either by Marcus Gearharts or in the style of Gearharts. That's still a bit in dispute. She was a very well-known court lady and beauty of her age. In fact, several engravings of her portraits made around. They're sort of the early modern equivalent of the polite pinup. Samuel Pepys, in fact, had a picture of her in his library, and we know that he always had an eye for the ladies. So I guess in early modern terms, she was really a bit of a babe, as it were. But she is has very distinguished lineage. Lister's father was her second husband. By her first husband, she is the grandmother of Sarah, Duchess of Marlborough. So Lister was born, obviously, to a very distinguished family with royal connections, but they also had connections to the world of medicine. Two of Lister's great uncles, Edward and this one here, Sir Matthew, were court physicians, and Sir Matthew Lister was childless, and he gave a lot of money and doted on his young great-nephew Martin. He paid for him to have education at St. John's College, Cambridge, where Martin Lister received his MA in 1655, and also paid for him to go to 3 years to Montpellier to study medicine and sort of do the grand tour, as it were. And this was a really pivotal thing for Martin Lister, because that's where he becomes a natural historian as well as a physician. He goes on simpling expeditions to find flora and fauna with friends of his, and he wrote a complete list of all the books that he read when he was abroad, which still exists. It's a wonderful gentleman's pocketbook or almanac with a handy comb case, and it still exists in the Bodleian Library, so you can really read about the grand tour of a young gentleman about ready to be a physician. He eventually does become a court physician for Queen Anne in 1702. He was also elected a Royal Society Fellow in 1670, and he devoted himself to a variety of biological studies, including, of course, the study of spiders, shellfish, fossils. He formed a friendship and a lengthy correspondence with another luminary of the early Royal Society, John Ray, who did some of the first complete catalogs of plants and birds extant in history. And he ultimately contributed over 50 papers to the philosophical transactions of the Royal Society. He was vice president of the Royal Society for 4 years, from 1683 to 87, when Samuel Pepys was president. Samuel Pepys was often called away on business in the Admiralty, so Lister, in the good vice presidential fashion, had to pinch hit for him quite often, so he's very involved in Royal Society business. When a fellow an officer, Lister did all sorts of work for the Royal Society. He sponsored, raised books on insects and birds, helped to identify species. He also played a huge role in the creation of this book here, the Historia Piscium, which I've been told is actually downstairs in the exhibit on flying fishes. If you have a chance to take a look at this, this was a monumental achievement of the early Royal Society. It is a lavish book, the best history of fishes of its time. It was incredibly expensive to make this book because of the plates that they had to do of each of the fishes. There's over 187 in this humongous folio-sized book. Now, what Lister's job is because the book was so expensive, he had to go around with the collection box to members of the Royal Society and say, okay, if you buy a picture of a fish and sponsor it, give me money, and you can have your name below the fish. So if you look through this book, you will see the names of, Robert Boyle, Christopher Wren, each of their names below a fish. Samuel Pepys actually sponsored 79 of these plates. So this was Lister's job, to go around and do this as vice president of the Royal Society. Now, he also sponsored Edward Cluyes' first book on fossils. Lister was charged to have the minerals cabinets constructed for the Royal Society repository, which was his first museum, because he knew a lot about fossils and minerals, and his opinions were very much respected. Now, the limited amount of scholarly work that's been done about Lister has primarily been as a spider man and as a mollusk man, the shell guy. But what this talk's going to concentrate upon is not only that work, but also some of his lesser-known achievements, as I've mentioned, in geology and in the modeling of data, because that's important too. Now, some of the reasons why Lister's many contributions as a natural philosopher may have been neglected, part of it was because of the way he was perceived in the popular imagination of his own time. He had a well-known penchant for assembling cabinets of curiosities. He loved to collect things. And he published upon a diverse variety of non-scientific topics, including memoirs and a cookbook. His work with insects and snails, so pioneering, was perceived by the public as kind of trivial, because they said, why do you want to spend all your time dissecting snails for? That seems a very silly thing for a physician to want to do. So vast is this collection of books and coins and statuary that when the Ashmolean Museum opened, it had a gold inscription on the door, and it said, Libri impressi et manuscripti et donis clarissimum verborum, Dr. Elias Ashmole e Martini Lister. And all that means is that it thanks both Martin Lister and Elias Ashmole for their contributions to the Ashmolean Society, or Ashmolean Museum. So Lister was very important in the formation of one of the first museums in England. There was even a scribnarium listerium in the Ashmolean, a specific room dedicated to everything that Lister had donated to the Ashmolean. Now, this made Lister a big target for satirists of virtuosi and scientists at this time. A lot of them were made fun of in the popular imagination for doing strange things like working on snails. William King lampooned this publication of Lister. Lister did an edition of the ancient Roman Apicius' cookbook, and which seemed he's just fascinated by classical authors, so he did this. And William King lampooned this cookbook, and especially with its references to contemporary English cuisine, humbly inscribed to the Honorable Beefsteak Club. The historian Geoffrey Carr notes that Shadwell, in his satirical play, The Virtuoso, which was performed in 1673, specifically poked fun at Martin Lister's penchant for studying spiders and ants. The visitor to the laboratory of the main character, Sir Nicholas Gimcrack, in The Virtuoso stated, "What does it concern a man to know the nature of an ant?" And another visitor replies, "Oh, it concerns a virtuoso, so it be knowledge, 'tis no matter of what." All right? So even when more modern scholars have studied Lister, they've sort of relegated him to the status of a minor natural historian interested in no matter of what, who devoted his time, as one said, to dissecting slugs, or as he called them, naked snails. And some scholars have called him an observer rather than a thinker. But I think these assessments are quite misleading about Martin Lister. Charles Raven, who wrote a wonderful biography of John Ray, said that Lister was a skillful observer and a pioneer of considerable importance. Practicing scientists continue today to use Lister's observations, and entomologists have recently recognized that Lister came very close to a biological definition of arachnid species, or to actually define what makes a spider. And it was Lister that discovered that silk drags spiders in the atmosphere. In other words, Lister made the discovery of a type of spider known as a ballooning spider. I'm going to go pass by that. A ballooning spider. This is Stegodyphus lineatus. This little guy shoots out silk, and it uses it to fly through the air in search of food. And Lister was the first person that watched this happen, and I found the quote to this. He writes a letter to John Ray. "Certainly, if you had been with me in September, I would have gladdened your heart with a delightful spectacle. I then, while collecting spiders, wanted to examine more closely those marvelous strands fallen from the sky, and in those investigations chanced upon this spider, which I had never seen before. Suddenly the one I was watching left off what it was doing, and bending backwards it pointed its anus into the wind and shot forth a thread in exactly the way a lusty lad expels urine from his swollen bladder. I was surprised at the creature's unusual behavior. Then I saw the thread stretched for many ells and waving in the air. Soon, however, the spider herself jumped upon it and was swept away, whether she was pulled by the thread which was still sticking firmly to her rear and was borne over some quite tall trees." Now, entomologists presently are constructing mathematical models to determine how turbulent air can propel these spiders much further than even Lister thought. They've realized they could go hundreds of kilometers out to sea. And as the entomologist Eric Duffy has indicated, the activity of spider ballooning is prevalent in the temperate regions of the northern hemisphere among a small species of the family Lineafidae, as well as among juvenile spiders from larger species. So in order to balloon, you have to be kind of tiny, all right, to get up in the air. The best flight times are on cloudy fall and summer days, when there are a combination of cooler temperatures and superior updrafts. And Lister had noted that this behavior is very season dependent, and spiders balloon to catch gnats and other prey. And this is what he wrote. He said, "In winter and at Christmas I have observed them busy a-darting, and few of them sail then, and therefore but single threads only to be seen. And besides, they are but the young ones of last autumn's hatch that are then employed, and it is more than probably that the great ropes of autumn are made only by the great ones, and upon long passages in summer weather, when great numbers of prey may invite them to stay longer up." Now, I looked at this observation, and I got a hold of an entomologist friend of mine by the name of Andy Reynolds, and he thought it was really interesting because he said that every day of the growing season, about 1,800 spiders land in each hectare of arable farmland after ballooning to eat gnats, and it is season dependent. Lister was absolutely right, and he said that if farmers can therefore predict the influx of spiders, they can reduce the amount of pesticides that they use on their land. So they're actually tracking when these guys decide to balloon and come and eat their prey, so they can lessen the amount of pesticides that they're using in farmland, which I think is really interesting. Now, what I'm going to show you here is a short video. It documents the work of Bob Suter, who's at Vassar College in the United States, and it shows some of his footage of ballooning spiders and the work that's being done with this. So you never thought you get to see spiders fly through the air today, but you get to. So we're going to see how this works.
Biophysicist Bob Suter is off on a spider hunt.
If we're going to catch any spiders out here that are ballooning, they're going to be falling past us downward because we're sitting still in the air and the spiders are falling down.
All they need to get airborne is an upward flow of air and a single strand of silk. Spiders are denser than air, but they can gain height if the air column is rising faster than gravity is pulling them down. Human balloonists need lots of hot air to keep them aloft.
We're actually neutrally buoyant, which means we're at the same density as the air that's around us. This whole system that we're in is at the same density. So we're sitting still. With respect to the air column, a spider is always falling through it. Let's see if we got anything on here. I got him? Yeah, I got him.
Size is an important factor in determining a spider's chance of getting airborne.
The forces important in spider ballooning really are gravity, because that acts on all objects no matter where they are, and the drag force created by air flowing past the spider.
The hot wire anemometer measures the speed of the air currents. The stream of smoke gives an indication of the direction of the airflow.
A spider that stands on the tip of a twig with silk in the air above it and is trying to balloon is going to become airborne only when the velocity of the air is high enough in an upward direction so that the drag the spider experiences exceeds the pull of gravity.
Because air currents are unpredictable and the next puff of wind could carry it up or down, the spider has to choose the right moment for takeoff.
These graphs show velocity of the wind here, the angle of the wind, and the probability that a spider can get airborne under those conditions. And so the angle of the wind is what I got from the smoke. The velocity of the wind came from that anemometer that I was using. And what basically this shows is that for all the variety of angles and all the variety of winds, there's a very small proportion of the time when the spider can actually get itself airborne. If you look at this in more detail, you can see how this works out for very small spiders, medium-sized spiders, and larger spiders. And what you see, of course, is that for the very large spider, this is 1.6 milligrams, becoming airborne is very difficult and only happens in a very small fraction of the time when conditions might be right for a medium spider. And of course, for a very small spider, 1/10 of a milligram, conditions are much more frequently ideal for getting airborne.
After takeoff, the direction they go depends entirely on the wind. But balloonists of all sizes have some control over the duration of their flight.
The way we're controlling our height right now is by burning propane into the air above us, which makes us less dense, so we go up, and we could vent some air or we could just let it cool down and we'd go down, adjusting how dense we are relative to the air around us.
Spiders can't adjust their density. What they can do is vary their surface area to increase or decrease the viscous drag.
Some of the work that I've been doing has shown that as they spread their legs out, they substantially increase the drag that they experience, so they fall more slowly. And if they pull their legs in, that is, crunch them up against their body, they can fall more rapidly.
And falling spiders make subtle use of ballooning silk.
The length of silk that they let out, or reeling up the silk, which they can do with their legs, can of course decrease or increase the amount of silk that's out there, and therefore decrease or increase the amount of drag that they're experiencing, but they're always falling.
Hot air balloon 5304 X-ray.
Great. All right, I'd like to thank the Open University and Professor Suter and also the BBC for allowing me to show that video. Felicity knows it was quite a process, but we got there in the end. Though Lister's subsequent paper to the Royal Society classifying English spiders, this is illustration of it, only contained 38 species, he was obviously wrong that there were that few of types of spiders in England. John R. Parker, the former president of the British Arachnological Society, remarked of Lister's works that really one can see the seeds of a modern system of classification 80 years before Linnaeus and his disciples. And Linnaeus, in fact, cited Lister's work on spiders extensively in his 10th edition of the System of Nature. One thing that you notice about Lister's scientific papers, too, there's a tremendously high standard of scientific illustration, and it was part of a practice of artistic excellence, among which are those called the York Virtuosi. Lister practiced medicine in York for 13 years, and he gathered around him sort of a salon of artists and other intellectuals, and they discussed different topics in sciences and the arts. This particular spider piece was done by an artist named William Lodge, the son of a very wealthy merchant in Leeds. Lister was also friends when he was in York with Francis Place, who invented the mezzotint, actually invented the process for it, and Henry Gillies, the glass painter. Gillies' work was in many of the colleges of Oxford and Cambridge. Later, Lister trained his two daughters, Susannah and Anna, how to do scientific illustration. In preparation for his master work on shells, the Historia Conchyliorum, done in 1685. Susannah and Anna did over 1,000 copper plates for this book, and they hand-colored them. And in fact, if you look at letters, the Lister papers, you'll see him writing his wife, and he'll tell them, now I'm bringing home some art supplies for the two girls, but don't let them touch them until I can show them what they have to do. And they worked for their father for about 10 years doing this book. Anna Lister, in particular, also did scientific illustration for some of the luminaries in the Royal Society, including Leeuwenhoek, who did the famous work on microscope observations, and she did the drawings for him. So these young ladies were powerful scientific illustrators in their own right. Not only did he pioneer elements of scientific illustration, conchology, and arachnology, but he had proficiency in botany. He has an orchid named after him, Listera Ovata, and of course, as you could guess, a spider, Pachygnatha listeri. He was a very handsome spider, I think. Lister's observations on English true bugs, or Hemiptera, have been discovered as recently as 2007 by entomologists as the first records of several species, as well as the first true locality records for British bugs. So entomologists are now, and I'm helping them do this, we're combing Lister's archives to see what we can find in his field observations, because we're finding out that we're finding new species this way, all the way back from a 17th century naturalist. I think Lister's reputation may also be on the rise because there's a lot more recent scholarship in the history of science and natural history. Zoology, botany, mineralogy, and other disciplines of natural history are perceived not as mere supplements to the work and physics of astronomy, of what we traditionally think of the scientific revolution of Newton, and no offense to Newton, but they were just as important. They were at the very core of early science. Further, early modern physicians were often prominent natural historians, and they imbibed a commitment to natural history as the best way of knowing. Lister wrote himself, "I must yet for my own part affirm that I am much beholden to the study of insects for the disciplining of my thoughts and the making of them readier in observing, if you will, useful and necessary things in medicine." So Lister saw the discipline of observation of insects as important for him to be a better doctor, which is a very interesting claim to make. As Rob Iliff has demonstrated in his study of gentlemen travelers in the early Royal Society, when Lister did journey to Montpellier for his medical training, he met many of these natural philosophers, cum physicians, such as Nicholas Steno. And so his interest and expertise in natural history was reflective of it becoming the foundation for a great deal of contemporary science, including medicine. I mean, natural history was the early modern equivalent of big science, and Lister was right there in the middle of it. He was therefore not a dilettante observing for the sake of observation like Shadwell's Nicholas Gimcrack, but his dedication to detailed empiricism was for an important purpose. And he stated in a letter to John Ray, which I love this quote, "For my part, I think it absolutely necessary that an exact and minute distinction of things precede our learning by particular experiments. What different parts each body or thing may consist of, likewise concerning the best and most convenient ways of separation of those parts, and their virtues and force upon human bodies and to the uses of life, all these besides the different textures are things subsequent to natural history." Now, that's an interesting slide to bring up after that, isn't it? Lister not only did work in mollusks and conchology, but he was interested in geology and the weather as well. Why was he interested in geology? Well, part of it was pragmatic reasons. Lister's family owned many leases on lands up north, primarily near Craven, Yorkshire, and they were iron and coal mines, and quite old iron and coal mines. And owning mines like this in the early modern period was a tricky business. It was very hard to make them profitable, and part of that was because of the safety concerns of the men that were working in these things. Lister's early letters reveal an interest in the causes of lethal damps. This is a phenomenon that occurs in mines. Damps could come in different varieties. There were suffocating mixtures of gases such as nitrogen and carbon dioxide. That was known as choke damp. You could have explosive vapors, which is known as fire damp, spontaneous explosions in mines. Lister suspected that these spontaneous explosions were, believe it or not, caused by the presence of these guys, iron pyrites or fool's gold. Now, why did he think that? Well, for a couple of reasons. I have a thing of fool's gold here, which I'm going to pass around, so you get to pass it a little sparkly. What I want you to do with it, though, is not just say, ooh, that's really pretty, but if you take it and you scratch it, right, and then you smell it, you're going to notice it has a really unique smell. It should smell a little bit like a match head. Sulfurous, because it's an iron sulfide, and it's quite pungent, right? Well, Lister did a whole lot of books speculating that the sulfurous exhalations of minerals like iron pyrites could actually cause spontaneous explosions in mines. Now, he had the right conclusion. It was the presence of these guys that caused mine explosions, but he kind of went up the wrong path. Actually, what happens is if you can have coal that's contaminated with these, and you strike the coal and the iron pyrite together, the pyrite will spark. And the spark hits the metal tool, and it will cause an explosion in the mine. And in fact, these things were used in wheel locks. They were used in early guns. So Lister's conclusion was right, just the way he got there was wrong. But the idea of sulfurous exhalations is important in this work, as we're going to see. He wondered, once he made these conclusions, whether if there was a geological pattern to where iron could be found. And so he wrote a book called A Method for the History of Iron, and I believe this is the first geological survey of iron deposits that was ever done. He classified about 30 different types, including hematite, and he included excerpts from accounts of mining technologies. For instance, if you take these things and you crush them up and you mix them with water and put it in the sun, you get sulfuric acid. You get very oil of vitriol, so he was interested in that sort of thing. He also considered knowing where iron was important because of work by earlier scientists such as William Gilbert, who wrote a book on the magnet. Gilbert thought that the Earth was mostly made of iron and it was a giant magnet, and its magnetism was what kept it spinning around in the air. So Lister, as a result, was quite interested to see where iron could occur in different parts of the United Kingdom. He also lived near, for a while, the geological scar in Yorkshire Dales, the Craven Scar. And this is a series of geological faults that has a tremendous amount of fossils and carboniferous limestone. So he gets very interested in geological matters and starts looking at strata. And if any of you go up there, what you'll notice, there's a pub called the Listera Arms, which is a tribute to the family, and they do have good beer, and that's indeed the family crest. So that was a new discovery for me. That was incredibly serendipitous. Now, taking all this information he thought about geological maps and strata, he makes a proposal in 1683 to the Royal Society. And it's a proposal for a new sort of maps of counties with tables of sands and clays, such chiefly are found in the northern parts of England. Now, he may have been influenced by his friend Nicholas Steno, the Dutch scientist, who ascribed the formation of strata to the gradual deposition of sediment in the sea. And Lister had met him when he was in Montpellier, so it's altogether likely that they may have talked about geological matters. Lister remarked that if we had such a map, we shall then be better able to judge of the make of the earth and of many phenomena belonging thereto, when we have well and duly examined it, beginning from the outside downwards. And as for more of the inward and central parts of the earth, I think we shall never be able to confute Gilbert's opinion, who will, not without reason, have it altogether iron. He proposed that soil types on this type of map could be represented by different colors and contour lines, and noted that the variety of sands and clays in England he saw varied according to height. Now, that was the proposal for the very first geological map, which was later done, but it took about 150 years for somebody to cotton on to it. What Lister didn't do, however, was a tying together of geological strata to fossil evidence. It was not because he was not aware of fossils. That's quite the contrary. He'd come across many fossilized mollusks in his expeditions, and he published the first paper on fossilized sea lilies, or crinoids. That's these little guys. I have an example fossil of one of these if you want to look at it. This is the stalk. These are interesting in their own right because the stalk, when it becomes fossilized, tends to separate. There's a little notochord that runs up the middle, sort of a nerve cord, and these little things here separate out from each other. They're found a lot in lindisfarnes, and they almost look like little beads when you pick them up on the beach, right, with a little hole in them. And so they're known as St. Cuddy's beads or St. Cuthbert's beads, because it was the idea that he strung them together to make a rosary. And so Lister actually looked at that legend and did the first paper on these fossil sea lilies. Now, we think, oh, you know, what a naturalist. He knew all about fossils. Well, he did, but he had a very different idea about what they were. He didn't think that fossil shells are the remains of living creatures, or fossils were the remains of living creatures. He thought they were what they were called formed stones, spontaneously created by nature. Many naturalists in this period postulated that metals and minerals were spontaneously nurtured or generated in deep mines, and stones that resembled living creatures could be generated without any organic origins. So we think of fossils as being remnants of living creatures, but 17th century investigators like Lister thought these stones could be created spontaneously by nature as part of her inherent powers. Now remember when I passed around the pyrites and it smelled, right? Well, he thought that the smell of the pyrites not only could cause explosions, but it had sort of mysterious force that could be sort of a plastic, vital force that actually could create stones in different shapes. And a lot of people believed this sort of thing at that time. Underground aquifers carried waters with generative seeds that in the heat below ground were thought to form rocks and minerals, and so they thought you could make these formed stones. Now, intriguingly, other stones that were so curiously wrought by nature, such as trilobites, had been found that didn't resemble any existing living creatures. You look at a lot of fossilized creatures and there's nothing in them that looks like things that were here now. And so that actually gave naturalists like Lister evidence. They said, see, they're just formed by nature. There's nothing like that now. This is before any conception of extinction, right? So this was evidence for them that they're just formed spontaneously by nature, right? Okay. Lister also saw fossilized conch shells that he saw resembled no living creatures he had encountered on a simpling expedition to gather specimens. So rock conchlites are no shells. And as he was the acknowledged expert in conchology, his words carried weight in the Royal Society. Though Lister's views were challenged by contemporaries such as Robert Hooke, who proposed that fossils were remnants of living creatures, as well as the hieroglyphics of nature that could be used to create a history of geology, the debate over fossil origins continued unabated in the society into the next century. For instance, only a few years after Lister, his friend Edward Clueth argued for fossils as guides to the age of the containing strata. He compared this method using one of Hooke's similes to dating a Roman monument from coins found in the ruins. Yet Clueth was not sure fossils were of animal or plant origins either. Since the Christian creed taught all species were created in Genesis, any ideas of species becoming extinct were considered heterodox. Despite these arguments over fossil origins, in the 19th century, Charles Lyell acknowledged that Martin Lister was the first to be aware of the continuity over large districts of the principal groups of strata in Britain. He provided a signpost for the research of future geologists. Now the last topic is interest in how to present data. Lister invented a method called the histogram graph to keep track of weather data that he recorded with his barometer. At the same time as he promised to bring in his table of clays and sands with samples of the things themselves to the Royal Society in 1683, he also showed the way which he had made use of the keeping his account of the barometer, which he approved of as very easy and convenient. He showed the book containing 3 years' account. Every table contained a month's account was printed off on a copper plate. And there's your plate, right? Every table containing a month's account was, the upper line contained the inches from 28 to 31. That's your readings of the barometer. Here's your days of the month, right? And he put a line over where the barometer rose and fell. So there's a line here. And then he connected this all together, right? That's a histogram. There it is, all right? He said the account for the whole month was but one line bending as the quicksilver rises or falls. And he claimed because he could do this, he could predict the weather 3 or 4 days hence. So he thought he was better than the Met Office, right? All right. Now, he used it for things, he was interested in the influence of the weather on sap flow in trees and how it rose and fell. But he also was interested in the connections between weather and health. He thought that, for instance, cold weather is more healthful because he says up north where it's colder, people live longer. He also looked at, well, we all know that, don't we? He also looked at insects, and he did some experiments with hibernating insects where he froze them and then he thawed them out, and he said, my goodness, they've actually gone in suspended animation, and they could live forever in suspended animation. Maybe being cold-blooded is healthier for you and leads to greater longevity than having warm blood. This may sound a little silly, but there are people all the time we hear about who are going to be frozen after their death, right? So this is interesting. The society took great note of this histogram method. They called it Lister's method. And Robert Plott, a colleague of Lister, said, if we do this, we will be enabled with some grounds to examine not only the castings, breadth, and bounds of the winds, but of the weather they bring with them, and probably in time thereby learn to be forewarned of emergencies, such as heats, colds, dearths, plague, and other distempers, which are now unaccountable to us, and by their causes be instructed for prevention or remedies. Some proposals in the Royal Society said, well, let's do a big weather chart and see if we can make it correlate to astrological phenomena. Maybe by making astrological predictions, we can predict the weather. Now, I know this sounds a bit strange, but this was the nature of thinking at this time. And somebody as eminent as Robert Boyle was also very taken by Lister's barometric method. We discovered this, Michael Hunter and I put 2 and 2 together, discovered this quite by chance in the Boyle papers, and here's Lister's barometric method. And Robert Boyle actually requested a number of these graphs from Lister, and he made records of the weather because he thought that it would be of good use. So though the Dutch polymath Christian Huygens had done basic graphs to present statistics about mortality in 1668, Lister's histogram method was really a pioneering representation of scientific data. So therefore, to conclude, an analysis of Lister's work demonstrates, I think, the value of thinking in an interdisciplinary manner to better comprehend the interactions in this period between disciplines as diverse as meteorology, geology, arachnology, conchology, and medicine. Although it's generally acknowledged that a major feature of early modern science was the rapid and exponential growth of natural history, it in fact would be more correct to talk of a proliferation of natural histories, in the plural, all with different philosophical pedigrees. I think if we tease out the differences as well as the overlapping assumptions of these natural histories, it will reveal connections between natural phenomena and the origin of ideas that early modern natural philosophers like Lister took for granted, but that we sometimes overlook. Thank you.